Welcome to Part 1 of Vectors and Transformations in the Cambridge IGCSE Mathematics 0580 syllabus. Today we will be covering the following subjects on screen. Let us start by answering the question, what are vectors? In mathematics, vector is a mathematical object that has both magnitude and direction. Displacement, velocity, and acceleration are all examples of physical quantities that may be represented by vectors. Generally, vectors are represented graphically as arrows, with the arrowhead representing the vector's direction and the length of the arrow representing the vector's magnitude. On printed paper, vectors are usually represented by bold, small letters like A or B. Another way to represent a vector is to write its starting and ending points with an arrow symbol over the top, like this.
Please keep in mind that while handwriting, you cannot easily write the vectors in bold characters, so either write them like this or use small letters with a line under them like this.
Translation is defined as a transformation in which every point of an object moves exactly the same distance in the same direction. For example, this shape, A, has been translated 6 squares to the right. Then 3 squares up to create shape, B. Translation vectors are defined as vectors that describe the displacement or change in position of an object in space.
On a two-dimensional grid, we can use the grid measurement to represent the translation vector as a column vector, with the top number representing the horizontal movement and the bottom number representing the vertical movement. For example, this translation vector could be written as a column vector like this. The horizontal movement is 6 units to the right, so it is positive 6, and the vertical movement is 3 units up, so it is positive 3. Please pause the video, take some time to write down the column vectors for each of the displayed vectors. Then verify your answer on the following slide.
Even if translation vectors are in different places on the same grid, they can still be equal as long as their horizontal and vertical units are the same. So, we can say here that vector AB is equal to vector CD, which is equal to vector EF. The magnitude of the vector, also known as the modulus, is represented by 2 vertical lines. For example, if I want to write down the magnitude of vector A, I will put it between 2 vertical lines like this, and pronounce the magnitude of vector A, or the modulus of vector A.
Excuse me, but how do we calculate the magnitude or modulus of a vector?
Okay, as long as the vector magnitude is equal to the length of that line, we can use Pythagoras' theorem to compute the vector magnitude. As a result, the magnitude of vector A will be equal to the square root of 8 square plus 6 square, giving a value of 10. In fact, vector addition can be thought of as a relay race where each vector represents a runner. Just as in a relay race, each runner completes their lap and passes the baton to the next runner, and so on. The result of the addition will be the straight line linking the start of the first runner to the finish of the final runner.
Please be careful of the result vector's direction. It starts at the start of the first vector and finishes at the end of the final vector. In addition, all of the vectors we add together are linked head to tail, as shown here.
In fact, you can think of subtracting one vector from another as adding a negative vector. Like what we are doing here. Other than adding and subtracting vectors graphically, we can also add and subtract vectors by adding or subtracting their corresponding horizontal and vertical values. Let us consider these two vectors, a and b. Let us add them together graphically. I'll begin by sketching vector a. First, I'll choose any point on the grid to be the vector tail. And then I'll move 1 unit to the right and 2 units up to find the vector head. Now I have vector A on the grid. I'll then draw vector B, starting from the head of vector A. Then I will move 2 units to the right, then 3 units down. Now we can draw the result of the addition of vectors A and B, a tail at the tail of vector A and a head at the head of vector B. We can also add vectors A and B by adding the values of A and B in the horizontal and vertical directions, as shown here. As you can see, the calculated solution matches the graphical solution, as it is clear from the graph that the resulting vector moves to the right 3 units and moves down 1 unit. Also, using the same method, we can subtract the vectors, like this. Let us confirm this result graphically. First, I'll choose any point on the grid to be the vector A tail. Then I'll move 1 unit to the right and 2 units up to find the vector head. From the head of vector A, we will move to the head of vector minus B, by moving 2 units to the left and 3 units up. Now we can draw the result of the subtraction, a tail at the tail of vector A and a head at the head of vector B. When a vector is multiplied by a positive scalar, its magnitude changes but its direction stays the same. If the number is negative, the vector's direction will change as well. As seen in the graph, when I multiply vector A by a positive 2, its magnitude doubles but its direction remains unchanged, and when I multiply vector A by a negative 2, its direction reverses as well. In addition, if the vector is expressed as a column vector, the scalar is multiplied by each of the numbers in the column vector, as in that example. In fact, I can use this example to describe the condition that must be met in order to declare two vectors to be parallel. Let's start by giving each of those vectors a unique name. We already know that these 3 vectors are parallel because they are the result of multiplying vector A by a scalar. In other words, if one of the vectors is a multiple of the other, then the 2 vectors are parallel. So in this set of vectors, vector B is parallel to vector A because vector B equals vector A multiplied by 2. And the same vector B is parallel to vector C because vector C equals vector B multiplied by a negative 1. So finally, vector A is said to be parallel to vector B if vector A equals k multiplied by vector B, where k is a scalar value.
Excuse me, but if I get any arbitrary vectors like the ones shown here, how can I tell if they are parallel or not? And if they are parallel, how can I calculate the value of k?
Okay, let's start by writing each of those vectors in column vector form. To generalize my answer, I will denote the x component of vector A as a sub x, and the y component as a sub y, and the same for vectors b and c. By definition, if a scalar value k multiplied by the vector a result in the vector b, then the vectors a and b are parallel. Therefore, in the event that k does exist, k multiplied by a sub x equals b sub x. And k multiplied by a sub y equals b sub y. As a result, k is equal to b sub x divided by a sub x and also equal to b sub y divided by a sub y. And that is the condition for parallel vectors. When you divide each vector component by its corresponding component in the other vector, you get the same value. So, if we apply this condition here, we will find that vector A is parallel to vector B, as shown here. Vectors, as we now know, are mathematical objects that specify magnitude and direction and do not have a definite starting point. We could represent vectors graphically by a line segment on a grid like this, but we can also move this vector anywhere on the grid and it will still be the same vector. However, in certain situations, we need to use vectors to specify the position of a point in space. That's where position vectors come in. For example, if we have a point P on this grid, we can define its location by a position vector that starts from the origin and ends at point P. It is important to notice that position vectors differ from other vectors in that they always begin at the origin rather than any random point on the grid. In this section, we'll put our understanding of vectors to use by applying them to a few geometrical problems. But first, let's go over some fundamental ideas, because they will be useful when solving geometrical problems with vectors. The first idea is an easy way to express a vector in terms of other vectors. Let us begin with a simple example to explain this idea. Consider the three vectors a, b, and c, as shown here, and I'd like to express vector c in terms of vectors a and b. The first thing I'll do is assign a letter to each point in the graph. Let's call them x, y, and z. I'll now define each vector by its start and end points. As a result, vector a becomes vector x, y, vector b becomes vector x, z, and vector c becomes vector z, y. To express vector c in terms of vectors a and b, consider the following. I want to travel from point z to point y, but instead of using vector c, I want to use vector b and vector a. Then let us express the journey in terms of vectors using the graph points, which will be vector z x plus vector x, y. Now I will go back and express it in terms of vectors a and b. Vector zx is in the opposite direction of vector b, which is xz, so this vector is equal to negative b. And vector x, y is vector a. As a result, vector c is equal to vector a minus vector b. The second idea is a simple method for dividing the vector into ratios. Let us use another simple example to demonstrate this idea. Consider the vector AB if point x divides it in the ratio 3:4. As a result, we now have two additional vectors, ax and xb. There is a simple rule for determining the relationship between those two vectors and vector AB, which gives us vector ax equal to the ratio of 3/7 multiplied by the vector ab, and vector xb equal to the ratio of 4/7 multiplied by the vector ab. However, in order to ensure that you don't forget that rule, let's figure out how to prove it. Because the vector ab is divided by point x in a ratio of 3:4, the first step will be to divide the vector ab into 7 equal sections. Then 3 of those sections will be for vector ax and the remaining 4 sections will be for vector xb. And for that vector, ax will be 3 out of 7 times the vector ab, while the vector xb will be 4 out of 7 times the vector ab. So, in general, if a point x divides a vector AB in the ratio p to q. Then vector AX will be equal to the ratio of p divided by the sum of p and q multiplied by the vector AB. And vector x b equals the ratio of q divided by the sum of p and q multiplied by vector AB. Before moving on to other ideas, I believe it will be more beneficial if we first apply those two ideas to solve some problems. Please pause the video, take your time, and do your best to solve the problem before looking at the solution. As given in the problem, we have 2 points on the grid, point A, which is located at the coordinates x equals 4 and y equals 2. And point B, which is at the coordinates x equals -3 and y equals 4. And this is what gives us our two position vectors from the origin, vectors OA and OB. And first, we need to obtain the vector AB. In order to do this, we need to move from point A to point B using the vectors AO and OB, as demonstrated in this animation. Alright, let's get started on the solution. The position vector OA corresponds to the coordinates 4 and 2, while the position vector OB corresponds to the coordinates -3 and 4. Vector AB equals vector AO plus vector OB. And that give us vector AB equals negative vector OA plus vector OB. Because vector OA is in the opposite direction of vector AO. And that give us vector AB at coordinates -7 and 6. And according to that, 2 vector AB will corresponds to the coordinates -14 and 12. This problem is from the May 2016 Cambridge International Examinations Past Paper Test, Paper 2 Variant 2. Please pause the video, take your time, and do your best to solve the problem before looking at the solution. To express vector CB in terms of vectors A, B, and C, we must travel from point C to point B via those vectors. As a result, vector CB will be equals to vector CO plus vector OA plus vector AB. Let us now express those vectors in terms of vectors A, B, and C. Vector CO has the same magnitude as vector C, but in the opposite direction, so it equals -C. Vector OA is the same as vector A, and vector AB is the same as vector B. Point Q divides vector CB with a 1-to-1 ratio, therefore, vector CQ is equal to 1 divided by 2 multiplied by vector CB. The position vector of point Q is the vector that begins at the origin and ends at point Q, which is vector OQ, and to obtain it, we must travel from point O to point Q via vectors OC and CQ. As a result, the position vector of point Q equals vector OC plus vector CQ. Vector OC is the same as vector C, and vector CQ equals half of vector CB. When we replace CB with its value, we get. Now, to arrive at the final answer, let's simplify this algebraic expression. Point P divides vector AB with a 2-to-1 ratio, therefore, vector PB is equal to 1 divided by 3 multiplied by vector AB. Vector PQ begins at point P and ends at point Q, so we must take this pass from point P to point Q to express it in terms of vectors A, B, and C. As a result, vector PQ equals vector PB plus vector BQ. Vector PB is 1/3 of vector AB, while vector BQ is half of vector BC. Replace those vectors with their values in terms of vectors A, B, and C, and we get. Simplify this algebraic expression to get the final answer. Please pause the video, take your time, and do your best to solve the problem before looking at the solution. Because point A divides vector CO in a 1-to-1 ratio. Then vector AO equals half vector CO, and the same vector OB equals half vector OD. Let us express vector CD and vector AB in terms of vector CO and OD. To express vector CD in terms of vector CO and OD, we must make this pass from point C to point D through vector CO and OD, as shown here. So, vector CD equals vector CO plus vector OD. And vector AB equals vector AO plus vector OB. AO equals half vector CO, and vector OB equals half vector OD. We get vector AB equals half vector CO plus vector OD. So, vector AB equals half vector CD, or vector CD equals 2 vector AB. And this means that first, vector AB is parallel to vector CD. Second, the length of vector CD equals 2 times the length of vector AB. Let us return to our fundamental concepts. To express a vector in terms of other vectors, imagine moving from the tail to the head of the vector, not through the vector itself, but through the other vectors you want to use to express the vector, and if you move in the opposite direction of the vector, it will take a negative sign, as in the example where vector C equals vector A and minus vector B. Finally, in our previous examples, I want you to try this concept again, but this time take a different route to obtain the vector PQ, and you will still get the same result. The second idea is dividing the vector into ratios. If a point x divides a vector AB in the ratio q to p, then vector AX will be equal to the ratio of q divided by the sum of q and p multiplied by the vector AB. And vector XB equals the ratio of p divided by the sum of q and p multiplied by vector AB. Now that we've covered the first and second ideas, let's move on to the third and final ideas we'll cover in that section. In the third idea, we will use vectors to prove whether 3 points are collinear or not.
Excuse me, what does it mean when we say 3 points are collinear?
Well, it simply means that these points lie on the same line. That's what collinear means. In fact, to prove that 3 points lie on a straight line, the vectors connecting the 3 points must be parallel. For example, if vectors CB and BA are proven to be parallel, then points A, B, and C are collinear. Okay, let's use vectors to prove that points A, B, and C are collinear. To start, I will draw the position vectors of points A, B, and C, and denote them as A, B, and C, respectively. Next, I will use these position vectors to find the vectors CB and BA. Vector CB is equal to the position vector of point B minus the position vector of point C. So, vector CB equals the column vector 3, 4 minus the column vector 9, 2 to get column vector minus 6, 2 as the result. And the same, vector BA is equal to the difference of the position vector of point A and the position vector of point B. So, vector BA equals the column vector minus 6, 7 minus the column vector 3, 4 to get column vector minus 9, 3 as the result. As we previously learned, Two vectors are considered parallel if they have the same direction, meaning their component ratios are equal. To determine if vectors CB and BA are parallel, we can compare the ratios of their components. The ratio of the x components of vector BA to vector CB is -9 divided by -6 is equal to 1.5. The ratio of the y components of vector BA to vector CB is 3 divided by 2 is equal to 1.5. Since the ratios of the components are equal, therefore, vectors CB and BA are parallel. Since point B is common to both vectors and both vectors are parallel, therefore, points A, B, and C are collinear. Thank you for taking the time to watch this video. If you have any questions about the material, please leave them in the comments section below and don't forget to like and subscribe. The following section of this series will go over translations, enlargement, rotation, and reflection.